Before July 1st, 2025, astronomers thought they understood interstellar visitors. We had two previous examples, clear theoretical models, and instruments capable of solving any mystery the cosmos could deliver. Then, 3I Atlas arrived, and our confidence evaporated like ice in sunlight. The more we study this object, the less sense it makes. It produces carbon dioxide at rates that should be impossible for its size. It maintains gas clouds that extend farther than Earth's orbit around the Sun. It shows chemical signatures that don't match any formation environment we can imagine. Each new observation forces us to question assumptions we thought were settled science. The world's most powerful telescopes are essentially admitting defeat against a chunk of rock and ice barely larger than a small city. What does it mean when our best science fails to explain something as simple as a comet? Join us as we explore why this visitor might represent either the most important discovery of our lifetime, or proof that the universe still holds secrets we're not ready to understand. Part 1. Why 3I Atlas just doesn't make sense. On July 1st, 2025, at precisely 14 hours, 37 minutes Universal Time, something changed the trajectory of our understanding of the cosmos. Not in some distant galaxy, not in the theoretical realm of academic papers, but right here in our own solar system. The Atlas Survey Station in Chile, a routine automated telescope scanning the skies for potentially hazardous asteroids, captured something that shouldn't exist. The object appeared as nothing more than a faint smudge against the star field, a moving dot at 4.5 astronomical units from our Sun's position. But within hours, the orbital calculations revealed a truth that sent ripples through the astronomical community. This visitor was traveling on a hyperbolic trajectory with an eccentricity far beyond one. In the language of celestial mechanics, this means it's unbound. It will never return to our solar system, ever. They designated it C/2025 N1 Atlas. But to those who study the wanderers between the stars, it became known simply as 3I Atlas, the third confirmed interstellar object to grace our cosmic neighborhood. The speed alone should have been our first clue that we were dealing with something extraordinary. 130,000 miles per hour. 209,000 kilometers per hour. That's not just fast by earthly standards, that's the fastest solar system visitor we've ever recorded. To put this in perspective, imagine a bullet traveling at typical velocity, then multiply that speed by 170. That's 3I Atlas, screaming through space with the momentum of an entirely different star system. But speed, as we would soon discover, was only the beginning of its mysteries. Within days of discovery, the Gemini North Telescope in Hawaii turned its 8-meter mirror toward this cosmic interloper. What it revealed defied our expectations of what an interstellar rock should look like. There, surrounding the invisible nucleus, was a fuzzy, compact coma, a cloud of dust and gas being actively released by solar heating. This wasn't some cold, dead fragment of interstellar debris. This thing was alive, breathing vapor into space as our sun's energy awakened dormant ices that had slumbered for millions of years in the cold between the stars. The implications struck the scientific community like a meteor. Here was an object that had traveled the galactic wilderness, surviving radiation that would sterilize any earthly organism, enduring temperatures just a few degrees above absolute zero. Yet, the moment our sun's warmth touched it, it began to sublimate, to transform directly from ice to gas, creating a ghostly atmosphere in the vacuum of space. But perhaps most unsettling was what this activity revealed about its orbital path. 3I Atlas wasn't just passing through our solar system, it was threading the needle between planetary orbits with surgical precision. Its closest approach to Earth would be 1.8 astronomical units, roughly 270 million kilometers. Safe, yes, but the geometry was almost too convenient, too perfect for observation. NASA immediately marshaled its most powerful instruments, the Hubble Space Telescope, the James Webb Space Telescope, the Swift Observatory, and the Transiting Exoplanet Survey Satellite. The European Space Agency coordinated global tracking efforts. This wasn't just another comet to catalogue, this was a messenger from another star system, carrying chemical signatures that could reveal the conditions in an alien planetary nursery. Yet, even as the world's most advanced telescopes turned their attention to this visitor, a troubling pattern emerged. Every observation seemed to raise more questions than it answered. The object's behavior matched no existing model of interstellar debris. Its chemistry defied conventional wisdom about comet composition, and its very presence in our solar system, traveling at such extreme velocity yet remaining active, suggested formation conditions unlike anything in our local cosmic environment. The irony wasn't lost on the researchers studying it. Here was an object from light years away, farther than human imagination could truly grasp, yet it would spend the next several months within the relatively familiar confines of our solar system. A cosmic visitor staying just long enough for us to study it, but moving so fast that every observation window was precious and fleeting. As July turned to August, and the first detailed images began streaming back from our most sophisticated instruments, one thing became crystal clear. 3I Atlas wasn't going to give up its secrets easily. If anything, the more we learned about it, the more mysterious it became. The stage was set for a chase against time itself, a race to understand this enigmatic wanderer before it disappeared forever into the cosmic dark, carrying its mysteries back to the space between the stars. Part 2. The Path Through Our Neighborhood. Picture the solar system as a vast clockwork, with planetary orbits marking predictable paths through space and time. Now imagine a bullet fired from another galaxy, streaking through this cosmic machinery at impossible speed, threading between the gears with mathematical precision. That bullet is 3I Atlas, and its trajectory through our neighborhood tells a story of cosmic timing that borders on the theatrical. The visitor's itinerary reads like a carefully planned tour of the inner solar system, yet it was written in the stars long before Earth existed. Perihelion, the closest point to our Sun, would occur on October 29th, 2025. Not the comfortable distance of most comets, but a scorching passage between the orbits of Earth and Mars, roughly 130 million miles from our star. Close enough for the Sun's energy to boil away ancient ices, yet far enough to avoid complete destruction. But here's where the cosmic choreography becomes almost cruel in its precision. As 3I Atlas makes its closest approach to the Sun, Earth will be positioned on the exact opposite side of our star. For nearly 2 months, from late September through early November, our visitor will be lost in the Sun's glare, invisible to every telescope on or orbiting Earth. It's as if the universe conspired to hide the most important moments of this interstellar encounter. The observational window tells a tale of astronomical frustration. Scientists have roughly 3 months to gather data before 3I Atlas vanishes behind our star, then perhaps 6 weeks after it emerges in December, before the object becomes too faint and distant for meaningful study. It's a deadline that would make any investigative journalist nervous, except these journalists are studying something that won't be back for another visit, ever. Yet the trajectory offers tantalizing opportunities for those willing to think beyond Earth's perspective. On October 3rd, 2025, 3I Atlas will streak past Mars at a distance of just 29 million kilometers. That's closer than Mars's own moons come to the planet. For the fleet of robotic explorers orbiting the red planet, including the Mars Reconnaissance Orbiter with its powerful high-rise camera, this presents an unprecedented chance to photograph an interstellar visitor from an alien vantage point. The geometry is everything in astronomy, and this geometry is both a gift and a curse. When 3I Atlas reappears in Earth's skies in early December, it will grace the pre-dawn hours in the constellation Virgo, climbing toward Leo as the weeks progress. But by then, it will be racing away from the Sun at over 150,000 miles per hour, growing fainter each night as it returns to the cosmic deep. For amateur astronomers hoping to glimpse this visitor from another star, the news isn't encouraging. At its brightest, 3I Atlas will barely reach magnitude 11 or 12, visible only through telescopes, appearing as nothing more than a faint, fuzzy star among millions of others. There will be no naked eye spectacle, no brilliant tail stretching across the sky like Comet Hale-Bopp or Neowise. This visitor prefers to keep a low profile. The orbital mechanics reveal another layer of the mystery. 3I Atlas isn't just moving fast, it's moving wrong. Its hyperbolic orbit suggests an origin velocity of roughly 25 kilometers per second relative to the local standard of rest. That's fast enough to escape not just our solar system, but potentially the gravitational embrace of our entire galactic neighborhood. This isn't some recently ejected debris from a nearby star formation region. This is something that has been wandering the galaxy for a very, very long time. As spring turns to summer 2026, 3I Atlas will make another significant passage, this time near Jupiter, in March. This distant encounter has already sparked proposals for redirecting NASA's Juno spacecraft, currently in orbit around the gas giant, to attempt an intercept. It's an audacious idea that would require precise orbital mechanics and perfect timing, transforming a mission designed to study Jupiter's interior into humanity's first close encounter with a confirmed interstellar visitor. But perhaps the most humbling aspect of this celestial schedule is what it reveals about our cosmic perspective. Here we are, tracking an object with instruments worth billions of dollars, coordinating observations across multiple space agencies, and marshalling the finest minds in planetary science, all to study something that will spend less than 2 years in our vicinity before disappearing forever into the galactic night. The path of 3I Atlas through our solar system isn't just a trajectory, it's a timeline of opportunity and limitation, of windows opening and closing according to the ancient laws of orbital mechanics. And every day that passes brings us closer to our final chance to solve the mystery of this wanderer from the stars. Part 3. First Looks. What Hubble Sees. When the Hubble Space Telescope first turned its unblinking eye toward 3I Atlas on July 21, 2025, the universe offered us a paradox wrapped in starlight. The image that emerged from Hubble's digital sensors was both familiar and utterly alien, a teardrop-shaped cocoon of dust and gas, glowing softly against the infinite black, yet possessing a geometry that no textbook had prepared us for. The technical details read like poetry written in the language of physics. The nucleus, the solid heart of this interstellar wanderer, remained stubbornly unresolved, appearing as nothing more than a bright point source buried within its own atmospheric shroud. But Hubble's exquisite optics allowed scientists to place an upper limit on its size, no more than 3.5 miles across, roughly 5.6 kilometers in diameter. To put this in perspective, that's smaller than most earthly cities, yet this tiny fragment of another star system was generating a coma that stretched thousands of miles in every direction. But here's where the familiar becomes strange. Hubble tracked the comet against the background stars, keeping 3I Atlas perfectly centered in its field of view. The result? The stars themselves appear as bright streaks across the image, creating an ethereal backdrop that makes the comet look like it's flying through a tunnel of light. It's a photographic technique that transforms scientific documentation into accidental art, revealing the relative motion that separates this visitor from everything else in our cosmic neighborhood. The coma itself tells a story of thermodynamics playing out on an interstellar stage. As 3I Atlas approached the Sun, crossing the 4 astronomical unit threshold where water ice begins to sublimate in earnest, the nucleus began shedding material in a process that had likely remained dormant for millions of years. The dust particles, liberated from their icy matrix, formed a roughly spherical cloud around the nucleus, but with a distinct elongation pointing away from the Sun's path. This wasn't random, this was physics in action. solar radiation pressure and gravitational forces sculpting the coma into its characteristic tear-drop shape. Yet something seemed off about the tail. In most comets, the antisolar tail, the stream of material blown away from the sun by radiation pressure, is prominent and easily visible. In 3I Atlas, this feature was puzzlingly subtle, almost hidden. Initial Hubble analyses suggested its presence but couldn't confirm it with confidence. The geometry seemed wrong, as if we were viewing the tail from an angle that compressed it into near invisibility. This ambiguity would persist until late August, when the Gemini South telescope in Chile captured deep images that finally revealed what Hubble had only hinted at. There it was, a faint but definite antisolar tail, extending away from the sun like a gossamer thread in the cosmic wind. The astronomer's telegram number 17363 made it official. 3I Atlas possessed the tail that theory demanded, but it was playing by its own rules of visibility. The dust loss rates provided another puzzle piece. Hubble's measurements showed that 3I Atlas was shedding material at rates comparable to solar system comets observed at similar distances from the sun's gravitational force. This might seem reassuring, evidence of normal, predictable behavior, except for one crucial detail. This object had been wandering interstellar space for epochs, exposed to cosmic radiation that should have altered its surface chemistry in fundamental ways. Yet here it was, behaving like a fresh comet on its first passage through the inner solar system. The resolution of Hubble's images, among the finest achievable from Earth orbit, revealed another layer of the mystery. While the telescope could constrain the nucleus size and map the coma's morphology, it couldn't resolve any surface features or rotation state. The nucleus remained a point source, its secrets locked behind the glowing veil of its own atmospheric emissions. We were studying this visitor through the fog of its own making, like trying to examine a lighthouse bulb while standing in its beam. Perhaps most intriguingly, Hubble's observations hinted at structure within the coma itself. The dust distribution wasn't perfectly smooth. There were subtle variations in brightness and density that suggested active regions on the nucleus surface. Somewhere beneath that shroud of vapor and dust, specific locations were venting material into space, creating the patterns Hubble detected. But without higher resolution or multiple viewing angles, those patterns remained as cryptic as ancient hieroglyphs. The photometry revealed another surprise. 3I Atlas was brighter than expected for an object of its estimated size, suggesting either a larger nucleus than the size constraints indicated, or a surface with unusually high reflectivity. Both possibilities raised questions about its composition and origin. Dark, carbon-rich materials would produce a faint object. Bright, icy surfaces would create the luminosity Hubble observed. But the spectrum of possibilities left too much room for speculation. As August progressed and 3I Atlas continued its approach toward the sun, Hubble's observations captured the dynamic evolution of the coma. The dust cloud was growing, expanding as solar heating intensified. Yet the nucleus remained unresolved, a cosmic tease that revealed just enough to confirm its strangeness without explaining its nature. The images would soon be joined by data from other instruments, each adding pieces to a puzzle that seemed to grow more complex with every observation. But Hubble had established the visual baseline. This was no ordinary chunk of interstellar debris. This was something that demanded explanation, something that challenged our understanding of what an interstellar visitor should look like. In the gentle darkness of space, 3I Atlas continued its ancient journey, now illuminated by our sun's light and scrutinized by humanity's finest instruments. Yet for all our technological prowess, the visitor remained essentially unknowable, a mystery dressed in starlight and wrapped in its own luminous breath. Part 4. The Chemistry Surprise. The universe has a way of keeping astronomers humble, and 3I Atlas was about to deliver a masterclass in cosmic humility. When the James Webb Space Telescope, humanity's most powerful infrared eye, first analyzed the visitor's spectral signature on August 6, 2025, the results shattered every expectation we had built from studying its predecessors. The numbers told a story that made no sense. Carbon dioxide to water ratio, 8 to 1, 8 to 1. To appreciate how extraordinary this measurement is, consider that most comets in our solar system show the opposite pattern. Water dominates their chemistry by factors of 10 to 100. Even the most water-poor comets rarely exceed carbon dioxide to water ratios of 2 to 1. Yet here was 3I Atlas, flaunting a chemical signature so extreme it placed it in a category of 1. But Webb's discovery was only the opening act. Between August 8th and 12th, the FEREX mission, NASA's Wide-Field Infrared Surveyor, turned its attention to this interstellar oddity and uncovered something that defied every model of comet behavior. The carbon dioxide emission wasn't confined to a small region around the nucleus. Instead, it extended outward for at least 348,000 kilometers, nearly 250,000 miles, creating the largest carbon dioxide coma ever mapped around any comet. Imagine the entire Earth-Moon system, then stretch that distance another 50%. That's the scale of 3I Atlas's carbon dioxide envelope, a ghostly sphere of gas large enough to swallow multiple planetary orbits. The sheer size of this emission region suggested processes operating on scales that challenged our understanding of cometary physics. The spectroscopic data painted a picture of chemical extremes. While Webb detected robust carbon dioxide emission lines, the water signature was strangely muted, so faint that some observers questioned whether 3I Atlas contained significant water ice at all. This stood in stark contrast to earlier reports from the Swift Observatory, which had detected hydroxyl radicals that typically indicate water photodissociation. Somewhere in the translation from ice to gas to hydroxyl, the water story was getting lost. FEREX added another twist to the chemical narrative. Its wide-field spectral mapping revealed absorption features at 1.5 and 2.1 micrometers, spectroscopic fingerprints consistent with water ice on the surface or in the near-surface layers. So the ice was there, locked in solid form, but something was preventing it from sublimating efficiently into the gas phase. The surface was holding secrets that the spectrum could only hint at. The contrast with previous interstellar visitors was striking. 2I/Borisov, discovered in 2019, had shown elevated carbon monoxide, not carbon dioxide, relative to water. That chemical signature suggested formation in a cold outer disk environment where carbon monoxide ice could condense. But carbon dioxide tells a different story. It forms at intermediate temperatures, in regions where water would be liquid or vapor, but carbon dioxide could still freeze out of the gas phase. The implications rippled through theories of planetary formation. If 3I Atlas formed near a carbon dioxide snow line in another star system, it might represent material from a zone analogous to the asteroid belt in our own solar system, a region too warm for water ice, but cold enough for carbon dioxide to condense. Such environments might be common around other stars, but we'd never sampled material from one before. The extended carbon dioxide cloud raised even more profound questions. How does a nucleus only a few kilometers across generate and sustain an emission region larger than most planetary orbits? The physics demanded either an incredibly active surface, far more active than anything we'd seen in solar system comets, or a fundamentally different mechanism for releasing gas into space. Some researchers proposed that 3I Atlas might be fragmenting, releasing carbon dioxide-rich chunks that continue to sublimate as they spread away from the main nucleus. Others suggested that the extended emission might result from solar-wind interactions with a pre-existing gas cloud, amplifying the apparent size of the active region. Both explanations stretched the boundaries of conventional comet science. The timing of these discoveries couldn't have been more dramatic. Just as 3I Atlas was approaching the optimal viewing window before solar conjunction, its chemistry was revealing itself to be unlike anything in our catalogue of interstellar objects. We were watching a unique chemical laboratory in motion, powered by our sun but carrying the frozen history of an alien planetary system. Yet the carbon dioxide dominance also carried a sobering implication. If this was typical of interstellar material, then our models of how planetary systems form and evolve might be missing crucial pieces. The chemical diversity of 3I Atlas, combined with the contrasting signatures of 1I/Oumuamua and 2I/Borisov, suggested that the galaxy harbors a population of ejected debris far more varied than our theories predicted. As August progressed towards September, and the observing window began to narrow, astronomers found themselves in possession of data that was simultaneously unprecedented and insufficient. The chemistry of 3I Atlas was clearly extraordinary, but whether it represented a new class of interstellar object or simply an extreme example of known physics remained an open question. The universe, it seemed, was determined to keep us guessing until the very last moment. Part 5. What we still don't know. 3 months after discovery, with some of the world's most sophisticated instruments trained on 3I Atlas, we find ourselves in the peculiar position of knowing too little about too much. Each observation has revealed new facets of this interstellar enigma, yet the fundamental questions that matter most remain tantalizingly unanswered. The nucleus size exemplifies our predicament perfectly. Hubble's imaging constrains the diameter to somewhere between 320 meters and 5.6 kilometers, a range so broad it encompasses everything from a large building to a small city. This isn't a failure of instrumentation, it's the inevitable consequence of studying an unresolved object shrouded in its own luminous atmosphere. The nucleus could be a compact, bright sphere or an elongated dark chunk tumbling through space. Without direct resolution, we're essentially guessing. The rotation state remains equally mysterious. Most small bodies in the solar system spin with periods measurable in hours, and their changing cross-sections create detectable brightness variations as they tumble. But 3I Atlas has proven frustratingly stable in its apparent brightness, showing none of the periodic variations that would reveal its spin rate or orientation. Either it's rotating very slowly, spinning nearly pole-on relative to Earth, or its surface features are remarkably uniform. Each possibility carries different implications for its origin and structure. The water question has evolved into something approaching scientific drama. Early observations by the Swift Observatory's ultraviolet and optical telescope detected hydroxyl radicals, typically a reliable indicator of water vapor being broken apart by solar ultraviolet radiation. The presence of OH suggested substantial water outgassing, fitting cometry expectations. But Spherex's subsequent mapping found the water signal surprisingly weak, setting upper limits that contradicted the Swift detections. Either the water is there but hidden by observational effects, or our understanding of hydroxyl production in cometry environments needs revision. The tail morphology adds another layer of uncertainty. The Gemini South detection of an anti-solar tail in late August finally confirmed what theory demanded: material being pushed away from the sun by radiation pressure. But why did it take months to clearly identify this feature? The tail's subtlety compared to typical comets suggests either unusually large dust grains that resist radiation pressure, or a viewing geometry that compresses the tail structure into near invisibility. Both explanations raise questions about 3I Atlas's fundamental nature. Activity patterns present perhaps the most intriguing unknown. The Hubble images show a sun-facing elongation of the coma, material apparently flowing toward our star rather than away from it. This counterintuitive geometry initially puzzled observers, until they realized that viewing angle can create optical illusions in three-dimensional gas flows. The apparent sunward drift might simply be our perspective on a complex three-dimensional outgassing pattern, or it might indicate something genuinely unusual about how this visitor releases material. The composition mysteries extend beyond the carbon dioxide dominance. While Webb and Spherex have mapped the major gas species, they've barely scratched the surface of trace chemistry. What about organic compounds, sulfur-bearing species, noble gases? Each trace constituent could provide clues about formation, temperature, radiation exposure, and the chemical environment of the parent planetary system. But detecting these species requires observation time that's rapidly running out. Perhaps most frustrating is our inability to study 3I Atlas's behavior around perihelion, the very time when solar heating should drive the most dramatic changes in activity and composition. The solar conjunction blackout means we'll miss the climactic moment when this visitor passes closest to our star. We'll only see the aftermath, like arriving at a theater after the final curtain call. The speed of 3I Atlas compounds every observational challenge. Ground-based telescopes must track at rates that push their pointing systems to the limits. Space-based instruments face scheduling constraints as the target moves rapidly across the sky. And the ever-increasing distance means that every week of delay results in significantly degraded signal-to-noise ratios for spectroscopic observations. The kinematics tell their own story of uncertainty. While the interstellar origin is confirmed beyond doubt, tracing 3I Atlas back to its stellar birthplace requires precise knowledge of its trajectory, knowledge that's limited by our brief observational window and the gravitational perturbations it has experienced during its passage through our solar system. The current best estimate suggests an origin in the galaxy's thick disk population, among stars that formed when the universe was perhaps half its current age. But that's educated speculation based on incomplete data. Even the basic question of what drives 3I Atlas's activity remains open. Is it sublimating ices, like a normal comet? Is it fragmenting under thermal stress? Could it be electrically charged, interacting with the solar wind in unusual ways? The extended carbon dioxide coma suggests activity on scales that simple sublimation models struggle to explain. As we approach the solar conjunction deadline, the mounting uncertainties create a peculiar scientific tension. We know enough about 3I Atlas to recognize its extraordinary nature, but not enough to understand what makes it extraordinary. The December reappearance will offer one final chance to solve the mystery, or confirm that some cosmic secrets are meant to remain hidden. The universe, it seems, is particularly fond of visitors who arrive with more questions than answers. Part 6. What counts as interstellar? The cosmos doesn't issue passports, but if it did, 3I Atlas would carry credentials from another star system. Understanding what makes an object truly interstellar requires diving into the mathematics of orbital mechanics, a language where eccentricity values and hyperbolic trajectories tell stories of cosmic wandering that span millions of years. In the precise terminology of celestial mechanics, any object with an orbital eccentricity greater than 1 is unbound from our solar system. It's following what mathematicians call a hyperbolic trajectory, a path that opens into infinity rather than closing into an ellipse. 3I Atlas has an eccentricity of approximately 1.7, meaning it's not just unbound, but traveling so fast that even Jupiter's massive gravitational influence can barely deflect its trajectory. But eccentricity alone doesn't tell the complete story. The truly diagnostic measurement is called V-infinity, the velocity an object would have relative to the Sun if it were infinitely far away, beyond the reach of solar gravity. For objects born in our solar system, this velocity is essentially zero. They're gravitationally bound and will eventually return, even if their orbits take millions of years to complete. 3I Atlas has a V-infinity of roughly 25 kilometers per second, confirming beyond doubt that it originated elsewhere. To appreciate this velocity, consider that Earth orbits the Sun at about 30 kilometers per second. 3I Atlas is moving nearly as fast relative to the solar system as our entire planet moves around our star. That's the momentum of another world entirely, the kinetic signature of a formation environment where different physics governed the dance of gravity and motion. The discovery process itself reveals how rare these interstellar visitors truly are. The ATLAS survey system, short for Asteroid Terrestrial Impact Last Alert System, consists of 4 robotic telescopes designed to scan the entire visible sky every 2 days, hunting for potentially hazardous asteroids. In nearly a decade of operation, scanning millions of square degrees and cataloguing hundreds of thousands of objects, Atlas has found exactly one confirmed interstellar visitor. The statistics are sobering. Interstellar objects are perhaps 1,000,000 times rarer than typical near-Earth asteroids. This rarity isn't necessarily because interstellar space is empty, quite the opposite. Theoretical models suggest that every cubic light-year of our galactic neighborhood should contain thousands of interstellar rocks, fragments ejected from planetary systems during their chaotic formation phases. The problem is detection. These objects are faint, fast, and follow trajectories that carry them through our inner solar system for only brief periods. By the time we spot them, they're often already racing toward the exit. The technological revolution in wide-field surveys has finally given us the tools to find these cosmic nomads. PanSTARRS, the Panoramic Survey Telescope and Rapid Response System, found one I/Oumuamua in 2017. The Catalina Sky Survey discovered 2 I/Borisov in 2019. Now Atlas has delivered 3I Atlas. Each discovery required automated systems capable of processing thousands of images per night, comparing them against stellar catalogues, and flagging the handful of moving objects that deserve human attention. The confirmation process follows a rigid protocol that would satisfy any court of law. Initial detection triggers rapid follow-up observations to establish orbital elements. Within days, observatories worldwide contribute positional measurements that constrain the trajectory. Orbital mechanics software calculates the best fit orbit, testing whether the motion is consistent with solar system origin or requires an interstellar explanation. Only when multiple independent analyses confirm hyperbolic motion and exclude all possible solar system parent bodies does an object earn interstellar designation. The naming conventions reflect this careful verification process. The I designation for interstellar comes only after thorough vetting: 1 I for Oumuamua, 2 I for Borisov, 3 I for Atlas. Each number represents not just a discovery, but a confirmed sample from the vast population of debris wandering between the stars. Yet these 3 confirmed visitors hint at a much larger population waiting to be discovered. The Rubin Observatory, currently under construction in Chile, will begin operations in 2025 with a survey capability that dwarfs all current systems combined. Its wide-field camera will map the entire southern sky every 3 nights, with sensitivity that could detect interstellar objects years before they reach perihelion. Theoretical estimates suggest Rubin might find anywhere from 1 to 70 interstellar visitors per year, transforming these rare cosmic accidents into routine scientific opportunities. The physics of interstellar designation carries profound implications. These objects are time capsules from other star systems, preserving chemical and isotopic signatures from planetary formation environments we can never visit. Each visitor is a laboratory sample delivered to our doorstep, carrying evidence about conditions around stars that might be hundreds of light years away and billions of years younger than our Sun is. The hyperbolic trajectories also mean we get only one chance to study each visitor. Unlike periodic comets that return for repeated observations, interstellar objects are fundamentally disposable encounters. The data we gather during their brief passage through our observational sphere represents the only information we'll ever have about these particular samples from the galactic debris field. As 3I Atlas continues its hyperbolic journey toward perihelion, its interstellar credentials are beyond question. The mystery isn't whether it comes from another star system. The orbital mechanics prove that conclusively. The mystery is what kind of star system could produce such an unusual wanderer, and what its strange chemistry reveals about planetary formation in environments utterly different from our own. Part 7. 3 Visitors, 3 Personalities. The universe has a peculiar sense of humor, and nowhere is this more apparent than in the rogues gallery of interstellar visitors that have graced our solar system. In less than a decade, we've hosted 3 confirmed guests from other star systems, each one arriving with a personality so distinct that they seem designed to confound every assumption we make about the space between the stars. First came 1I/Oumuamua in 2017, the cosmic equivalent of a stone-faced stranger walking into a small-town bar. No visible coma, no tail, no outgassing that telescopes could detect, just a tumbling, cigar-shaped object that reflected sunlight like polished metal. Its behavior was almost aggressively normal until it began accelerating away from the sun without explanation. The acceleration was small but measurable, about 1/10,000th of Earth's gravity, yet it violated every expectation of how inert rocks should behave in space. The scientific community erupted in debate. Some proposed exotic mechanisms: hydrogen outgassing from subsurface ice, radiation pressure on an unusually reflective surface, even more speculative ideas involving solar sails or electromagnetic effects. The acceleration was real, multiple observatories confirmed it, but its cause remained maddeningly elusive. 1I/Oumuamua had turned gravitational physics into a mystery novel, leaving behind more questions than answers when it vanished into interstellar space. Then came 2I/Borisov in 2019, arriving like a familiar friend bearing exotic gifts. Here, finally, was an interstellar visitor that behaved like a proper comet. Bright coma, prominent tail, steady outgassing of water vapor and dust, all the features that astronomers expected from a chunk of primordial ice. But Borisov carried its own chemical surprise, an abundance of carbon monoxide that far exceeded anything seen in solar system comets. Its carbon monoxide to water ratio suggested formation in an environment colder than the outer reaches of our own system, perhaps around a star with a more extended disk of icy material. Now 3I Atlas has arrived as the third act in this interstellar drama, and its chemistry reads like a deliberate attempt to confound the patterns we thought we were beginning to understand. Where Oumuamua showed no gas, and Borisov showed elevated carbon monoxide, 3I Atlas dominates with carbon dioxide. The progression, no detectable outgassing, to carbon monoxide excess, to carbon dioxide dominance, suggests a sampling of formation environments so diverse that each visitor might as well come from a different universe. The morphological contrasts are equally striking. Oumuamua's elongated, tumbling silhouette suggested either a natural fragment or something more geometric in origin. Its 10:1 length-to-width ratio was extreme even by asteroid standards, leading to speculation about whether it might be artificially shaped. Borisov, by contrast, appeared thoroughly conventional, a roughly spherical nucleus surrounded by a symmetric coma and sporting a textbook anti-solar tail. 3I Atlas splits the difference in the most puzzling way possible. Its coma is compact and roughly spherical, suggesting a solid nucleus rather than a fragmented structure. But the subtle tail that finally emerged in late August imaging is strangely muted compared to Borisov's prominent plume. The geometry suggests controlled, localized outgassing rather than the explosive activity typical of comets approaching perihelion. The size estimates for each visitor tell their own story of diversity. Oumuamua stretched roughly 400 meters in length, but only 40 meters in width, a cosmic needle. Borisov's nucleus was estimated at roughly half a kilometer across, typical for a mid-sized comet. 3I Atlas falls somewhere between these extremes, with an upper size limit of 5.6 kilometers, but potentially much smaller. Each visitor samples a different scale of debris from the interstellar population. Perhaps most intriguingly, the three visitors arrived with completely different apparent brightnesses and discovery circumstances. Oumuamua was found when it was already racing away from the Sun, discovered almost by accident during routine asteroid surveys. Borisov was spotted while still approaching the outer solar system, allowing months of advance preparation. 3I Atlas was caught at the sweet spot, far enough out to plan observations, close enough to begin detailed study immediately. The chemical signatures hint at formation in three distinct environments. Oumuamua's lack of detectable outgassing might indicate processing by interstellar radiation, complete devolatilization, or formation in an unusually dry region of its parent system. Borisov's carbon monoxide enhancement suggests birth in the cold outer reaches of a protoplanetary disk. 3I Atlas's carbon dioxide dominance points to intermediate formation temperatures, perhaps in a zone where water existed as vapor, but carbon dioxide could still condense. The behavioral differences extend beyond chemistry to fundamental physics. Oumuamua's mysterious acceleration suggested forces beyond simple gravitational attraction, whether from outgassing too subtle to detect, radiation pressure on an unusual surface, or mechanisms we haven't yet identified. Borisov followed predictable comet physics, its trajectory precisely matching the gravitational models with no unexplained deviations. 3I Atlas so far appears gravitationally well behaved, but its extended carbon dioxide coma challenges our understanding of how small nuclei can generate such enormous gas clouds. The observational bias effects are profound. What we see depends entirely on geometry, timing, and the sensitivity limits of our instruments. Oumuamua's lack of visible activity might have looked very different if we'd caught it during an active phase. Borisov's textbook appearance might have seemed strange if we'd observed it from a different angle. 3I Atlas's subtle tail might be far more dramatic when viewed from Mars's perspective during the October encounter. Yet these three personalities, the mysterious accelerator, the carbon monoxide classical comet, and the carbon dioxide enigma, already hint at the vast diversity waiting to be discovered. If the first three interstellar visitors are this different from each other, what will the next dozen reveal? Each visitor is like a core sample from a different planet formation environment, carrying chemical fingerprints that encode the thermal history and composition of alien worlds we'll never see. The progression from Oumuamua to Borisov to 3I Atlas reads like the universe is systematically challenging every assumption we hold about what interstellar debris should look like. Just when we thought we understood the category, along comes another visitor to rewrite the rules entirely. As 3I Atlas approaches its date with solar conjunction, we're left to wonder whether its strange personality represents the tip of an even stranger iceberg, or whether we're simply learning that the space between the stars is far more chemically diverse than we ever imagined. Part 8. The Dynamics Puzzles. The universe has a way of hiding its most important secrets in the smallest deviations from expectation, and nowhere is this more apparent than in the subtle dance of forces that govern how interstellar visitors move through our solar system. The story of 3I Atlas is, at its core, a story about physics in motion, about tiny accelerations that could reveal profound truths about the nature of matter in the space between stars. 1I/Oumuamua established the template for interstellar mystery when it began accelerating away from the Sun in a manner that defied gravitational models. The effect was tiny, roughly 10 micrometers per second squared, about 1/10,000th of Earth's surface gravity, but it was persistent and measurable across weeks of observation. Multiple observatories confirmed the acceleration's reality, transforming what should have been a straightforward gravitational problem into a puzzle that continues to generate research papers years later. The acceleration wasn't random. It followed a specific pattern that suggested outgassing from the sun-facing hemisphere. But here's where Oumuamua became truly confounding. No telescope could detect the gas or dust that should accompany such outgassing. The object was accelerating like a comet, but looking like an asteroid, creating a contradiction that forced astronomers to consider increasingly exotic explanations. Some researchers proposed that Oumuamua might be outgassing hydrogen, a gas so tenuous and difficult to detect that it could explain the acceleration without creating a visible coma. Others suggested that radiation pressure on an unusually reflective surface could account for the observed motion. The most speculative hypotheses involved artificial origins, though these remained far outside mainstream scientific consensus. 3I Atlas, by contrast, has so far shown no comparable acceleration anomaly. Its trajectory matches gravitational predictions within observational uncertainty, following the smooth hyperbolic path that Newton's laws demand. But this apparent normalcy might be misleading. The non-gravitational forces that affected Oumuamua became apparent only during extended observation as the object moved away from the sun's gravity. 3I Atlas is still approaching perihelion, and the most telling measurements may come during and after its closest solar approach. The chemistry of 3I Atlas suggests that if non-gravitational forces do emerge, they might follow a very different pattern than Oumuamua's hydrogen outgassing hypothesis. Carbon dioxide sublimation produces much more massive molecules than hydrogen, creating momentum transfer that's easier to detect but operates through different physics. If 3I Atlas begins showing measurable acceleration, it could provide the key to understanding whether Oumuamua's behavior was unique or represents a common feature of interstellar visitors. The viewing geometry adds layers of complexity to any dynamical analysis. Anti-solar tails can appear compressed or even invisible depending on our line of sight relative to the comet's motion. The sun-facing coma elongation that Hubble detected in 3I Atlas initially puzzled observers who expected material to flow away from the sun rather than toward it. But three-dimensional gas dynamics can create optical illusions where material moving in complex patterns appears to flow in counterintuitive directions when projected onto the two-dimensional plane of the sky. The extended carbon dioxide coma presents its own dynamical puzzle. How does a nucleus only a few kilometers across maintain an active emission region stretching hundreds of thousands of kilometers? The physics demands either an extraordinarily active surface, perhaps 100 times more productive per unit area than typical solar system comets, or a mechanism that distributes gas-producing material across a much larger volume than the nucleus itself. One possibility is that 3I Atlas is actually a loose aggregate of smaller fragments, each one outgassing independently to create the extended emission region. But if this were the case, we might expect to see evidence of fragmentation in the images, multiple brightness peaks, or elongated structures that would betray the presence of discrete chunks. So far, Hubble's high-resolution imaging shows no such features. Another explanation involves the interaction between outgassing and solar wind. As carbon dioxide molecules escape from the nucleus, they can be ionized by solar ultraviolet radiation, creating a population of charged particles that interact with the solar magnetic field. These electromagnetic forces could accelerate the gas to much higher velocities than simple thermal expansion, potentially explaining the enormous extent of the carbon dioxide cloud. The rotation state of 3I Atlas remains unknown, but it could hold crucial clues about dynamical processes. Most small bodies tumble chaotically due to outgassing torques, jets of gas that act like tiny rocket engines, gradually changing the object's spin state. If 3I Atlas is outgassing as vigorously as its extended coma suggests, it should be experiencing significant torques that would show up as brightness variations in long-term photometry. Yet the photometric record shows remarkable stability, with none of the periodic brightness changes that would indicate tumbling motion. This could mean the object is spinning very slowly, is viewed nearly pole-on so that rotation doesn't change its apparent cross-section, or has a surface so uniform that rotation produces no detectable brightness variations. Each possibility carries different implications for the object's structure and origin. The TESS observations, data from the Transiting Exoplanet Survey satellite, have hinted at possible activity even at the large distances where 3I Atlas was first detected. If confirmed, this would suggest that the visitor was already active when it was farther from the Sun than Jupiter, implying either an unusually volatile composition or a triggering mechanism beyond simple solar heating. As 3I Atlas approaches perihelion, the dynamical questions will only intensify. Will it show the mysterious acceleration that characterized Oumuamua? Will its coma morphology reveal the jet structures that would explain its extended gas cloud? The answers could redefine our understanding of how interstellar matter behaves when it encounters a star system very different from its birthplace. The physics is playing out in real time, written in the language of orbital mechanics and spectral signatures. We're watching dynamics that began in another star system millions of years ago, finally reaching their climax in the warm embrace of our Sun's gravity well. Part 9. The Global Watch. Who's observing what? When? The astronomical community has transformed 3I Atlas into the most intensively monitored interstellar visitor in history, orchestrating a global observation campaign that reads like a symphony of science played across multiple continents and orbital platforms. Every major space agency and ground-based observatory has joined what amounts to humanity's most coordinated effort to understand a single small object racing through our cosmic neighborhood. NASA Science Mission Directorate established the coordination framework, organizing a multi-mission approach that leverages every available asset. The Hubble Space Telescope provides the highest resolution imaging, tracking morphological changes in the coma and setting constraints on nuclear size that no ground-based instrument can match. The James Webb Space Telescope delivers infrared spectroscopy with sensitivity that can detect trace gases at concentrations measured in parts per million. The Swift Observatory monitors ultraviolet emissions that reveal the photochemical processes breaking apart molecules in the coma. The Ferrex mission has emerged as an unexpected hero in this observational campaign. Originally designed to map the infrared sky for cosmological studies, its wide-field capability proved perfect for tracing the enormous carbon dioxide cloud surrounding 3I Atlas. The synergy between Webb's high-resolution spectroscopy and Sferex's wide-field mapping has created a complete picture of both chemical composition and spatial distribution, data that no single instrument could have provided alone. Ground-based observatories worldwide have coordinated their efforts through the International Astronomical Union's Rapid Response Networks. The Gemini North Telescope in Hawaii captured the initial images that revealed 3I Atlas's compact coma. Its twin, Gemini South in Chile, provided the late August deep imaging that finally confirmed the subtle anti-solar tail. The Palomar Observatory's next-generation Palomar survey contributes ongoing photometry and astrometry, tracking brightness changes and refining the orbital solution with each observation. But the observational timeline is dominated by an unavoidable astronomical fact: solar conjunction. As 3I Atlas approaches perihelion on October 29, 2025, Earth's position relative to the Sun creates a viewing geometry that's both frustrating and poetic. Just as this interstellar visitor reaches its most active phase, it will disappear behind our star's glare, invisible to every Earth-based instrument for nearly 2 months. This blackout period represents one of astronomy's most maddening coincidences. The time when solar heating should drive 3I Atlas to its maximum activity, when its nucleus temperature peaks and outgassing rates reach their climax, will be completely unobservable from our planet. We'll miss the crescendo of this cosmic performance, left to study only the overture and the aftermath. The reappearance in early December will mark the beginning of the final act. 3I Atlas will emerge in the pre-dawn sky, positioned in the constellation Virgo before climbing toward Leo as the weeks progress. By then, it will be racing away from the Sun at velocities exceeding 150,000 miles per hour, growing fainter each night as it returns to the interstellar medium. The post-perihelion observations will be a race against time and distance, with signal strength declining exponentially as the visitor recedes. Yet this challenging timeline has inspired creative solutions that showcase the ingenuity of modern space science. The Mars Reconnaissance Orbiter's High-Resolution Imaging Science Experiment, HiRISE, represents a unique opportunity to observe 3I Atlas from an alien perspective. On October 3, 2025, the visitor will pass within 29 million kilometers of Mars, potentially allowing orbital assets to capture images during Earth's observational blackout. The resolution wouldn't rival Hubble's clarity, but it would provide crucial data during the period when Earth-based telescopes are blind. Several spacecraft currently traveling through the outer solar system have been identified as potential contributors to the observation campaign. NASA's Psyche mission, en route to a metallic asteroid, will pass within roughly 0.3 astronomical units of 3I Atlas on September 4, 2025. The European Space Agency's JUICE spacecraft, bound for Jupiter's moons, could attempt long-range observations during its November 4 approach. Even the OSIRIS-APEX mission has been considered for possible imaging starting in late 2025, though the geometric constraints remain challenging. The coordination extends beyond traditional astronomical assets. Radio telescopes worldwide are monitoring for any electromagnetic emissions that might indicate electrical activity or unusual interactions with the solar wind. Planetary radar systems are attempting to bounce signals off the nucleus, hoping to constrain size and rotation rate through echo delays. Even amateur astronomy networks have been mobilized to contribute photometric observations that help fill gaps in professional coverage. The international cooperation has produced observation scheduling that resembles military logistics. Time allocation committees at major observatories have granted emergency observing slots, disrupting carefully planned research programs to accommodate this cosmic opportunity. Data sharing agreements ensure that spectroscopic observations from one telescope can be immediately correlated with imaging from another, creating scientific synergies that multiply the value of each individual observation. The European Space Agency's Planetary Defence Office has coordinated tracking efforts that extend far beyond scientific curiosity. While 3I Atlas poses no threat to Earth, the techniques being developed to monitor its trajectory and predict its behavior will prove invaluable for future planetary defense scenarios. Every measurement of position and velocity contributes to orbital models that could someday help protect our planet from less benign visitors. As the observational window narrows towards solar conjunction, the intensity of global monitoring has reached fever pitch. Telescope time, that typically requires years of competitive proposals, is being allocated on weekly schedules. Data analysis that usually takes months is being compressed into days. The astronomical community has essentially declared 3I Atlas a cosmic emergency, not because it poses any danger, but because it represents an opportunity that will never come again. The December reappearance will test every aspect of this global coordination. Can we maintain the same level of intensive monitoring when the object is fainter and more distant? Will the post-perihelion chemistry reveal the secrets that pre-perihelion observations could only hint at? The next few months will determine whether this unprecedented observational campaign yields the breakthrough insights that could redefine our understanding of interstellar space. Part 10. Could we fly to it? The romantic notion of chasing down an interstellar visitor with a hastily launched spacecraft crashes hard against the unforgiving mathematics of orbital mechanics and the cruel realities of rocket science. Yet the very impossibility of intercepting 3I Atlas has inspired some of the most creative mission design studies in recent memory. Proposals that push the boundaries of what's theoretically possible with existing technology. The fundamental problem is time and velocity. 3I Atlas was discovered when it was already racing toward the inner solar system at over 200,000 kilometers per hour. Any intercept mission would need to match not just this enormous velocity, but also the precise vector, the direction and orientation of that velocity in three-dimensional space. The energy requirements for such a trajectory place it firmly in the realm of science fiction with our current propulsion technology. A dedicated interceptor mission launched from Earth would require delta-v, change in velocity, measurements that exceed the capabilities of our most powerful rockets by factors of 10 or more. Even if we could somehow generate the necessary thrust, the travel time to reach an intercept point would stretch into years, by which time 3I Atlas would be long gone, disappearing into interstellar space beyond the reach of any conceivable pursuit. But impossibility has never stopped aerospace engineers from dreaming, and several research groups have explored what might be achievable using spacecraft already in motion through the solar system. The Psyche mission, currently en route to study a metallic asteroid, will pass within 0.3 astronomical units of 3I Atlas on September 4, 2025. While Psyche wasn't designed for comet encounters, its instrumentation package includes cameras and spectrometers that could, in principle, gather valuable data during the flyby. The JUICE mission, the European Space Agency's Jupiter Icy Moons Explorer, presents another opportunity for serendipitous science. JUICE's trajectory will carry it within observation range of 3I Atlas on November 4, 2025, during the period when Earth-based telescopes are blinded by solar conjunction. The spacecraft's advanced imaging and spectroscopy suite could provide crucial data during this observational gap, though the encounter geometry and operational constraints remain significant challenges. Perhaps the most audacious proposal involves NASA's Juno spacecraft, currently orbiting Jupiter and studying the gas giant's interior structure. A research team led by astronomers at the Harvard-Smithsonian Center for Astrophysics has calculated that a carefully timed trajectory modification could redirect Juno toward a March 2026 encounter with 3I Atlas. The plan would use Jupiter's massive gravity field as a cosmic slingshot, adding velocity through an Oberth maneuver that leverages the spacecraft's proximity to the giant planet. The Juno intercept proposal reads like space mission fantasy made manifest. The spacecraft would need to execute a precisely timed burn while deep in Jupiter's gravity well, using the gas giant's orbital energy to accelerate toward an intercept trajectory. The timing would be critical, miss the window by hours, and the encounter becomes impossible. Execute the maneuver perfectly, and Juno could become humanity's first probe to conduct a close flyby of an interstellar visitor. But such proposals remain firmly in the analysis stage, hampered by operational realities that extend far beyond orbital mechanics. Juno's current mission is scheduled to end in 2025, and any trajectory modification would require approval from NASA headquarters, extensive mission planning, and likely congressional oversight. The spacecraft's aging systems and limited fuel reserves add additional constraints to an already challenging proposal. The Mars encounter on October 3, 2025, offers perhaps the most realistic opportunity for close-range observations. As 3I Atlas passes within 29 million kilometers of the Red Planet, the Mars Reconnaissance Orbiter's HiRISE camera could potentially capture images at resolutions approaching 30 kilometers per pixel. While this wouldn't rival Hubble's clarity, it would provide a unique perspective during the crucial period when Earth-based observations are impossible. The OSIRIS-APEX mission, originally designed to study the asteroid Apophis, has been mentioned in several academic papers as a potential contributor to 3I Atlas observations starting in late 2025. The spacecraft's suite of instruments, designed for close proximity asteroid science, could provide unprecedented detail about an interstellar visitor's surface properties and composition. However, the mission timeline and trajectory constraints make such observations highly speculative. Looking toward the future, the European Space Agency's Comet Interceptor mission represents humanity's best hope for a dedicated interstellar visitor encounter. Scheduled for launch in 2029, Comet Interceptor is designed as a rapid response mission that can redirect toward targets of opportunity, including newly discovered interstellar objects. The spacecraft will wait in a gravitationally stable orbit, ready to launch toward whatever cosmic visitor happens to arrive next. The academic literature on interstellar intercept missions has exploded since Oumuamua's discovery, with papers exploring everything from solar sails to fusion rockets to gravitational assist trajectories that leverage multiple planetary encounters. These studies serve as feasibility assessments for future opportunities, establishing the technological and logistical requirements for missions that don't yet exist but might someday become reality. The energy requirements for interstellar intercepts reveal just how different these visitors are from typical solar system targets. Where a mission to Mars requires delta V of roughly 6 km per second and a Jupiter flyby needs about 12 km per second, intercepting an object like 3I Atlas would demand delta V values approaching 50 km per second or more. That's beyond the capability of chemical rockets, requiring either nuclear propulsion, solar sails, or propulsion technologies that remain theoretical. Yet the scientific payoff from a successful intercept would be transformational. Close-range measurements of an interstellar visitor could reveal isotopic ratios that encode the stellar environment where it formed, surface compositions that preserve the chemical conditions of alien planetary disks, and structural properties that indicate how small bodies survive the journey between star systems. Such data would be worth decades of ground-based observations, providing ground truth for theories about planetary formation in environments utterly different from our own. The cruel irony is that each interstellar visitor represents a laboratory sample delivered to our doorstep, yet moving too fast for us to properly collect it. We're like researchers watching valuable specimens parade past our laboratory window, tantalizingly close, yet impossible to capture with current technology. As 3I Atlas continues its hyperbolic journey toward perihelion, the intercept studies serve as both frustrating reminders of our current limitations and inspiring blueprints for future possibilities. We may not be able to chase this visitor, but we're learning how to be ready for the next one. Part 11. Why carbon dioxide? Natural explanations on the table. The cosmic chemistry of 3I Atlas reads like a recipe from an alien cookbook, dominated by carbon dioxide in proportions that challenge every model we've developed for understanding how comets should behave. Yet, before we venture into exotic explanations, the laws of physics offer several natural pathways that could produce such an unusual chemical signature, each one revealing something profound about the conditions where this visitor was born. The carbon dioxide snowline hypothesis provides perhaps the most elegant explanation for 3I Atlas's unusual chemistry. In any protoplanetary disk, different volatiles condense at different distances from the central star, creating chemical zones as distinct as climate belts on Earth. Water ice dominates the cold outer regions, but carbon dioxide has its own freezing point at intermediate temperatures. An object forming just inside the water snow line, but outside the carbon dioxide snow line, would incorporate abundant CO2's ice while remaining relatively water-poor. This scenario places 3I Atlas's birth in a region roughly analogous to our asteroid belt, warm enough that water existed as vapor, but cold enough for carbon dioxide to freeze out of the gas phase. Such an environment would produce exactly the chemistry we observe: abundant carbon dioxide ice with only minor water contamination. The formation zone would be a cosmic sweet spot, governed by thermodynamics that favor carbon-bearing volatiles over hydrogen-oxygen compounds. But stellar environments vary dramatically from system to system, and the carbon dioxide dominance might reflect more exotic formation conditions. Stars with different masses and luminosities create different temperature profiles in their surrounding disks. A low-mass star might push the carbon dioxide snow line much closer to the central star, creating a larger zone where carbon dioxide ice dominates over water. Conversely, a particularly luminous star might create temperature gradients that favor carbon dioxide formation through entirely different chemical pathways. Radiation processing offers another compelling explanation for 3I Atlas's strange chemistry. During its millions of years wandering interstellar space, this visitor has been exposed to cosmic radiation at levels that would be lethal to any earthly organism. High-energy particles can break apart molecular bonds, rearrange chemical structures, and even create entirely new compounds through radiolysis. Radiation-induced chemistry that operates like a cosmic laboratory running experiments at the molecular level. Such processing could explain both the carbon dioxide dominance and the apparent water deficiency. Cosmic rays might preferentially destroy water ice while leaving carbon dioxide relatively intact, or they might convert simple organics into carbon dioxide through complex reaction networks. The reddish coloration that Spherex detected in 3I Atlas's spectrum is consistent with radiation processing, suggesting that its surface has indeed been chemically altered during its interstellar journey. The insulating crust hypothesis addresses one of the most puzzling aspects of 3I Atlas's behavior. Why does it show such strong carbon dioxide emission while water signatures remain stubbornly weak? Laboratory studies of analog materials reveal that organic rich mantles can form on icy surfaces, creating insulating layers that suppress volatile sublimation in selective ways. If 3I Atlas developed such a crust during its interstellar journey, water ice might be abundant beneath the surface, but prevented from reaching the gas phase by the overlying material. Carbon dioxide, being more volatile than water at the same temperature, could escape through cracks or thin spots in this insulating layer, creating the observed emission pattern. This would explain why Webb detects abundant carbon dioxide gas while Ferrex sees evidence for water ice in the solid phase. The water is there, but it's trapped below a surface layer that selectively allows carbon dioxide to escape. The icy fragments hypothesis, proposed by researchers studying the extended gas cloud, suggests an entirely different mechanism. Rather than a single solid nucleus, 3I Atlas might be a collection of carbon dioxide-rich ice chunks held together by weak gravitational and cohesive forces. As solar heating intensifies, these fragments could separate and sublimate independently, creating the enormous carbon dioxide coma through distributed outgassing across a much larger volume than a single nucleus could produce. This fragmentation model would explain several puzzling observations simultaneously: the extended gas cloud, the stable brightness despite apparent high activity, and the subtle tail morphology that suggests large-grain dust production. If 3I Atlas is essentially a flying gravel pile of carbon dioxide ice, its behavior would indeed be unlike anything in our catalogue of solar system comets. Temperature dependence provides yet another piece of the puzzle. At 3I Atlas's current distance from the Sun, roughly 2.5 to 3.5 astronomical units, water ice sublimation is relatively inefficient, while carbon dioxide remains highly volatile. The thermodynamics naturally favor carbon dioxide outgassing over water vapor production, potentially explaining the observed emission ratios without invoking exotic formation environments or unusual surface processes. As 3I Atlas continues warming during its approach to perihelion, this temperature dependence offers a testable prediction. If the carbon dioxide dominance results simply from thermodynamic effects, then post-perihelion observations should show increased water emission as the nucleus temperature peaks and begins to decline. The carbon dioxide to water ratio should evolve in predictable ways that match laboratory measurements of ice sublimation rates at different temperatures. The grain size effects in the coma and tail provide additional clues about 3I Atlas's composition. The subtle antisolar tail that emerged in late August suggests either unusually large dust particles that resist radiation pressure or a unique grain composition that affects how material responds to solar wind forces. Laboratory studies of carbon dioxide ice sublimation show that it can produce dust aggregates with different properties than water ice sublimation, potentially explaining the unusual tail morphology. Each natural explanation for 3I Atlas's chemistry opens windows into the physics of planetary formation in environments we can never directly observe. Whether formed near a carbon dioxide snowline, processed by interstellar radiation, or representing a fragment population with unusual volatile composition, this visitor carries information about stellar disk conditions that expand our understanding of how planetary systems develop. The natural pathways are numerous, testable, and grounded in well-understood physics. Yet their very abundance creates its own puzzle. With so many plausible explanations available, how do we determine which one, or which combination, actually describes the truth about this particular wanderer from the stars? Part 12. Where could it have come from? Tracing 3I Atlas back to its stellar birthplace is like attempting to solve a murder case where the crime scene is light years away and the evidence is encoded in orbital mechanics that stretch across galactic timescales. Yet hidden within the visitor's trajectory are kinematic clues that point toward a specific population of stars, and by extension, a specific epoch in our galaxy's formation history. The thick disk hypothesis has emerged as the leading contender for 3I Atlas's origin story. Our Milky Way galaxy consists of several distinct stellar populations: the thin disk where our Sun resides, containing relatively young stars rich in heavy elements; the thick disk, populated by older stars that formed when the galaxy was perhaps half its current age; and the ancient stellar halo, containing the galaxy's oldest and most metal-poor stars. Each population moves through space with characteristic velocities and orbital patterns that reflect the gravitational environment where they formed. The velocity vector of 3I Atlas, its speed and direction relative to the local standard of rest, suggests membership in the thick disk population. These stars formed roughly 8 to 12 billion years ago, during what cosmologists call the epoch of cosmic noon, when star formation rates throughout the universe peaked and heavy element production was rapidly enriching the interstellar medium. If 3I Atlas originated in this stellar environment, it represents material that has been wandering the galaxy since before Earth existed. The thick disk origin carries profound implications for understanding planetary formation in the early universe. Stars in this population formed from gas clouds with lower abundances of heavy elements than our Sun's birth environment. The reduced metallicity would have affected the composition of any protoplanetary disks, potentially favoring carbon-bearing volatiles over oxygen-rich species in ways that could explain 3I Atlas's unusual chemistry. But the origin story extends beyond simple stellar demographics to include the violent processes that eject material from planetary systems in the first place. Gravitational interactions with giant planets can scatter smaller bodies onto hyperbolic trajectories, launching them into interstellar space with velocities that depend on the specific geometry of the encounter. Close stellar flybys can similarly disrupt planetary systems, stripping away outer disk material that becomes the raw material for the interstellar debris population. The ejection mechanisms create a natural selection effect in the interstellar medium. Only objects with specific size ranges, compositions, and structural properties can survive the violent ejection process and the subsequent millions of years of interstellar travel. 3I Atlas represents a survivor of this cosmic winnowing process, carrying chemical and physical signatures that encode both its formation environment and its survival history. Population studies based on the 3 confirmed interstellar visitors reveal a sampling bias that complicates any attempt to infer origin stories. We've detected one object with no visible outgassing, one with carbon monoxide enhancement, and one with carbon dioxide dominance. This might represent the true diversity of interstellar debris, or it might reflect the particular detection biases of our current survey systems. Objects with different size distributions, activity patterns, or approach geometries might remain invisible to our telescopes. The galactic context adds another layer of uncertainty to origin stories. 3I Atlas has been traveling through space for millions of years, during which time it has experienced gravitational perturbations from every star system it has passed. These encounters have gradually modified its trajectory, erasing the kinematic fingerprints that would allow precise backtracing to its point of origin. We can identify the general stellar population it likely came from, but pinpointing the specific star system may be impossible with current data. The chemical clues provide more specific constraints on formation environment. The carbon dioxide dominance requires temperatures and pressures that exist only in particular zones around forming stars. If 3I Atlas condensed from the gas phase in a protoplanetary disk, the thermodynamic conditions must have favored carbon dioxide over water, suggesting either unusual disk chemistry or formation at a specific orbital distance where these conditions naturally arise. Isotopic ratios could provide the smoking gun evidence for 3I Atlas's origin, but measuring isotopes in such a faint, distant object pushes current spectroscopic techniques to their absolute limits. Different stellar environments produce different isotopic signatures in their planets and debris, creating chemical fingerprints that could identify not just the type of star system where 3I Atlas formed, but potentially the specific stellar mass, age, and metallicity of its parent star. The Rubin Observatory's Legacy Survey of Space and Time, beginning operations in the coming years, promises to transform origin studies from anecdotal case studies into statistical science. With the capability to detect dozens of interstellar visitors per year, Rubin will build a sample large enough to reveal population trends and chemical patterns that single objects like 3I Atlas can only hint at. Early claims in some media outlets about an extragalactic origin for 3I Atlas appear to be unfounded speculation rather than scientific consensus. The kinematic evidence points firmly toward a Milky Way origin, most likely from the thick disk population. While the galaxy is vast beyond human comprehension, it's not infinite, and the orbital mechanics place clear constraints on how far 3I Atlas could have traveled while maintaining its observed trajectory. The timing of 3I Atlas's arrival in our solar system might be pure coincidence, or it might reflect deeper patterns in galactic dynamics that we don't yet understand. If the thick disk origin is correct, then 3I Atlas represents material ejected from a planetary system billions of years ago, wandering the galaxy through cosmic dark ages. surviving supernovae and stellar evolution events that reshaped the galactic environment multiple times over. As we study this visitor's chemistry and dynamics, we're essentially conducting archaeology on galactic scales, inferring the properties of ancient planetary formation environments from the debris they left behind. 3I Atlas is a time capsule, but one that has been tumbling through space for so long that its contents have been altered by processes we're only beginning to understand. The December observations, when 3I Atlas emerges from solar conjunction, will provide crucial tests of origin hypotheses. If the post-perihelion chemistry shows predictable evolution based on thermodynamic models, it will support formation scenarios based on conventional ice physics. If the chemistry remains stubbornly anomalous, it might indicate formation processes or subsequent processing that exceeds our current theoretical framework. Part 13. The Avi Loeb chapter, Open, Minded, and Controversial. In the landscape of modern astronomy, few figures generate more passionate debate than Avi Loeb, the Harvard astrophysicist whose willingness to entertain unconventional hypotheses has made him both a lightning rod for controversy and a voice for scientific open-mindedness. His analysis of 3I Atlas exemplifies this complex legacy, meticulous in its observational foundation, yet bold to the point of provocation in its theoretical implications. Loeb's engagement with 3I Atlas began almost immediately after discovery, manifesting in a series of detailed essays that tracked the visitor's evolving observational signature with the precision of a detective following leads. His August 27th analysis proved particularly prescient when it claimed to detect the faint anti-solar tail that conventional observations had missed. Within days, the astronomer's telegram number 17363 confirmed exactly what Loeb had predicted. The subtle tail structure was real, visible to those willing to push their data analysis to the limits of detectability. But Loeb's interpretation of 3I Atlas extends far beyond confirming the presence of conventional cometary features. His size estimates, derived from brightness assumptions and scattering models, suggest a nucleus potentially tens of kilometers across, dramatically larger than Hubble's upper limit of 5.6 kilometers. This discrepancy isn't merely academic, it implies fundamentally different physics governing how this object interacts with sunlight. Either Loeb's brightness models are incorrect, or 3I Atlas possesses optical properties unlike any object in our solar system. The Ferrex spectral mapping data provides the foundation for some of Loeb's most striking claims. The vast carbon dioxide coma, extending nearly 250,000 miles from the nucleus, represents a scale of activity that challenges conventional outgassing models. Loeb emphasizes that such extensive gas production from a small nucleus requires either extraordinary activity levels or mechanisms that distribute gas sources across a much larger volume than traditional comet models predict. His interpretation of the water detection controversy illustrates the methodical approach that characterizes his analysis. Early swift observations suggested significant water vapor production based on hydroxyl radical detections, but Sferex's subsequent mapping found water signatures well below detection thresholds. Rather than dismissing either result, Loeb synthesizes them into a coherent narrative. 3I Atlas might contain water ice in its interior, but surface processes are preventing efficient sublimation, creating the observed discrepancy between expected and detected water signals. Where Loeb's analysis becomes genuinely controversial is in his exploration of what he terms technological hypotheses for 3I Atlas's behavior. Drawing on the precedent of 1I/Oumuamua's unexplained acceleration, he examines whether conventional physics can fully account for the visitor's extended carbon dioxide coma and unusual brightness properties. His calculations suggest that purely natural outgassing might struggle to explain the enormous gas cloud, leading him to consider whether additional energy sources could be contributing to the observed activity. The self-luminosity hypothesis represents perhaps Loeb's most provocative suggestion. If 3I Atlas possesses internal energy sources beyond simple solar heating, whether from radioactive decay, electrical phenomena, or more exotic mechanisms, it could maintain activity levels that natural sublimation processes cannot explain. Such internal energy could power the extended carbon dioxide production while remaining undetectable through conventional astronomical observations. Loeb's trajectory analysis adds another layer of intrigue to his technological hypotheses. He notes that 3I Atlas's path through our solar system displays geometric properties that optimize its observational opportunities from Earth, almost as if the trajectory were designed for maximum scientific impact. While this could certainly result from chance, the universe contains no shortage of cosmic coincidences. Loeb argues that we should at least consider whether such optimal geometry might indicate intentional navigation. The Intercept mission proposals that Loeb has co-authored represent perhaps his most concrete contribution to 3I Atlas science. Working with spacecraft trajectory specialists, he has outlined detailed scenarios for redirecting NASA's Juno mission toward a March 2026 encounter with the visitor. These proposals include specific burn timing, delta-V requirements, and scientific instrument capabilities that could provide unprecedented close-range data about an interstellar object. Yet even Loeb acknowledges the speculative nature of his more exotic hypotheses. His essays consistently frame technological explanations as alternatives to be tested rather than conclusions to be accepted. The scientific method demands that we consider all possibilities consistent with observational data, even those that challenge conventional assumptions about what interstellar debris should look like. The media response to Loeb's 3I Atlas analysis has followed predictable patterns, with headlines about possibly hostile technology that distort his carefully qualified speculations into sensationalized claims about alien visitation. Such coverage misrepresents both Loeb's actual arguments and the scientific process of hypothesis testing. Loeb proposes technological scenarios not because he believes them to be true, but because they represent testable alternatives to conventional explanations. His approach to 3I Atlas exemplifies a broader philosophy about how science should engage with anomalous data. Rather than forcing observations into existing theoretical frameworks, Loeb advocates for expanding those frameworks to encompass possibilities that might initially seem implausible. This methodology has historical precedent. Many breakthrough discoveries in astronomy began with observations that didn't fit conventional models. The testing protocols that Loeb outlines for distinguishing between natural and technological hypotheses provide a roadmap for resolving the 3I Atlas mystery through observational data rather than theoretical preference. High-cadence photometry could reveal whether the object's brightness varies in ways consistent with artificial illumination. Spectroscopic monitoring could detect emission lines that indicate exotic chemical processes. Close-range spacecraft encounters could measure properties that are impossible to determine from astronomical distances. Loeb's collaboration with mainstream observational teams demonstrates his commitment to evidence-based inquiry rather than speculative theorizing. His size estimates and chemical interpretations are grounded in the same data that other researchers analyze, though his willingness to explore unconventional explanations often leads to different conclusions. The scientific debate about 3I Atlas has been enriched by this diversity of perspectives, even when those perspectives generate controversy. The temporal pressure surrounding 3I Atlas observations adds urgency to Loeb's arguments about hypothesis testing. With only months remaining before the visitor disappears forever into interstellar space, the window for gathering decisive evidence is rapidly closing. If technological hypotheses are to be tested, the tests must happen now, during the brief period when 3I Atlas remains accessible to our most powerful instruments. As the solar conjunction approaches and observational opportunities dwindle, Loeb's analysis serves as both a scientific contribution and a philosophical statement about the nature of astronomical inquiry. His willingness to consider possibilities that other researchers avoid reflects a broader question about how science should respond to genuinely anomalous data, whether we should prioritize conventional explanations that fit existing models or remain open to explanations that might revolutionize our understanding of what's possible in the universe. The 3I Atlas controversy may ultimately be remembered not for the specific hypotheses it generated, but for the scientific methodology it exemplified. The careful balance between healthy skepticism and genuine open-mindedness that allows science to progress beyond the boundaries of current knowledge. Part 14. What could confirm or falsify theories next? The approaching solar conjunction of 3I Atlas creates a natural experiment in astronomical patience, but the December reappearance will trigger one of the most intensive observational campaigns in the history of small-body astronomy. The tests that await our interstellar visitor represent nothing less than a scientific trial by fire, where competing hypotheses about its nature will face the ultimate jury, observational reality. The post-perihelion spectroscopy holds the key to resolving the chemistry mysteries that have defined 3I Atlas since discovery. If natural sublimation physics governs this visitor's behavior, then the carbon dioxide to water ratio should evolve predictably as it moves away from the Sun's gravity. The nucleus temperature will have peaked during the unobservable perihelion passage, potentially breaking through any insulating surface layers that might have suppressed water vapor earlier in the approach. December and January spectra should show increased water emission if such suppression mechanisms are operating. Conversely, if the carbon dioxide dominance persists unchanged through perihelion, it would suggest either a genuinely water-poor composition or mechanisms that maintain the chemical imbalance regardless of temperature. Such persistence would challenge conventional models of cometary volatile evolution and potentially support more exotic explanations for 3I Atlas's behavior. High-cadence light curve observations represent another crucial test of competing hypotheses. If 3I Atlas is a conventional nucleus undergoing normal outgassing, its brightness should show predictable patterns related to rotation, state, and jet activity. Most active comets display brightness variations on timescales of hours to days as rotating surface features alternately face toward and away from the Sun's position. The absence of such variations would suggest either unusual uniformity in surface composition or viewing geometry that minimizes rotational modulation. More dramatically, any evidence of artificial illumination or non-thermal emission would show up as brightness variations that don't correlate with solar heating or geometric effects. Such signatures would be extraordinarily difficult to fake through natural processes, providing potentially decisive evidence for more exotic explanations. The photometric monitoring during December and January will essentially place 3I Atlas under continuous surveillance, recording every fluctuation in brightness that could reveal its fundamental nature. Resolved imaging campaigns using Hubble and large ground-based telescopes will trace the evolution of coma morphology as 3I Atlas responds to its perihelion encounter. Natural outgassing models predict specific patterns of dust release and tail development that should become more prominent as the visitor moves away from the Sun's position. The shape, orientation, and growth rate of any tail structures will provide detailed tests of whether 3I Atlas follows conventional cometary physics or operates according to different rules. The Mars-adjacent observations on October 3rd represent a unique opportunity to study 3I Atlas from an alien perspective during Earth's observational blackout. If Mars Reconnaissance Orbiter's HiRISE camera can capture images during the close approach, the data would provide crucial constraints on coma structure and activity patterns during the period when thermal stress peaks. The viewing geometry from Mars will be completely different from Earth's perspective, potentially revealing asymmetries or directional effects that are invisible from our vantage point. Opportunistic spacecraft observations could provide the most definitive tests of 3I Atlas's nature. The Psyche mission's September encounter, JUICE November observations, and potential OSIRIS-APEX imaging in late 2025 each offer the possibility of close-range measurements that ground-based telescopes cannot achieve. Spacecraft data could resolve the nucleus directly, measure magnetic field interactions, and detect particle emissions that would distinguish between natural and artificial origins. The James Webb Space Telescope's follow-up observations will push infrared spectroscopy to new limits of sensitivity and spectral resolution. Webb's ability to detect trace organic compounds, measure isotopic ratios, and map the three-dimensional structure of gas emission could provide the chemical evidence needed to distinguish between formation scenarios. If 3I Atlas shows isotopic signatures characteristic of the early galaxy, it would support the thick disk origin hypothesis. Anomalous isotope ratios might indicate processing by exotic mechanisms during its interstellar journey. SPHERICS's continued mapping of the carbon dioxide cloud will test whether the extended emission region grows, shrinks, or maintains its enormous size as 3I Atlas moves through different solar environments. Natural outgassing models predict specific relationships between heliocentric distance and coma size that should be observable if conventional physics governs the visitor's behavior. Perhaps most importantly, any detection of non-gravitational acceleration would provide crucial constraints on the mechanisms driving 3I Atlas's activity. The precision astrometry needed to detect such effects requires months of continuous tracking, comparing observed positions against pure gravitational models. If acceleration anomalies emerge, their magnitude and direction could distinguish between conventional outgassing effects and more exotic force sources. The synthesis of multiple observational approaches, chemistry, dynamics, morphology, and photometry, will converge on conclusions that no single technique could reach independently. Natural explanations for 3I Atlas's behavior make specific, testable predictions about how these different observables should correlate. Technological hypotheses predict different patterns of correlation, creating decision trees where observational reality can guide us toward truth. The December through March observation window represents humanity's final opportunity to understand this particular interstellar visitor. After that, 3I Atlas will fade beyond the detection limits of even our most powerful telescopes, carrying its secrets back to the cosmic deep. The observational tests that await our visitor represent both scientific opportunity and scientific responsibility, the chance to add another crucial data point to our understanding of the universe, and the obligation to pursue that understanding with rigor and open-mindedness. The universe has delivered 3I Atlas to our cosmic doorstep for reasons we may never fully understand. Our response to this gift will determine whether we emerge from this encounter with expanded knowledge or simply expanded mystery. Part 15. The Bigger Picture. Preparing for the next one. The story of 3I Atlas extends far beyond a single interstellar visitor racing through our solar system. It represents the opening chapter of a new era in astronomy, where the space between stars transforms from empty void into a populated realm of wandering worlds and cosmic debris. As we struggle to understand this particular visitor, we're simultaneously laying the groundwork for studying dozens more that await discovery in the coming decades. The Rubin Observatory's legacy survey of space and time stands poised to revolutionize our understanding of interstellar populations through sheer statistical power. Beginning full operations in 2025, Rubin's 8.4-meter mirror and 3.2 gigapixel camera will map the entire southern sky every 3 nights, achieving sensitivity levels that dwarf current survey capabilities. Theoretical estimates suggest this cosmic census could detect anywhere from 0 to 70 interstellar visitors per year, depending on the true size distribution and activity patterns of the galactic debris population. The transformation from anecdotal discoveries to statistical samples will fundamentally change how we approach interstellar visitor science. Instead of treating each object as a unique mystery, we'll begin to identify patterns, correlations, and population trends that reveal the underlying physics of planetary system formation and evolution across the galaxy. 3I Atlas, along with Oumuamua and Borisov, will serve as the calibration dataset for this new statistical approach to studying alien debris. The European Space Agency's Comet Interceptor mission represents humanity's most ambitious attempt to prepare for the next interstellar visitor. Scheduled for launch in 2029, this innovative spacecraft will position itself at the gravitationally stable Lagrange point L2, roughly 1.5 million kilometers from Earth, where it will wait in readiness for targets of opportunity. When the next interstellar visitor arrives, and statistical projections suggest it's only a matter of time, Comet Interceptor could redirect toward an intercept trajectory within months rather than years. The mission design philosophy behind Comet Interceptor acknowledges the fundamental challenge of studying fast-moving interstellar visitors. We need to be ready before they arrive, not scrambling to respond after discovery. The spacecraft will carry a suite of instruments designed specifically for high-speed encounters with pristine objects, including cameras capable of resolving surface features, spectrometers that can analyze composition during brief flybys, and dust analyzers that can capture and examine the actual material being shed by interstellar visitors. The rapid response framework being developed for interstellar visitors has applications that extend far beyond pure science. The same survey systems that detect cosmic wanderers also monitor for potentially hazardous asteroids, creating synergies between planetary defense and interstellar research. The techniques being refined for tracking 3I Atlas, rapid orbit determination, multi-observatory coordination, and flexible telescope scheduling will prove invaluable for responding to any future impact threats. The public engagement challenges surrounding interstellar visitors require careful balance between scientific honesty and responsible communication. Each new discovery triggers media speculation about alien origins, creating opportunities for both education and misinformation. The 3I Atlas experience has demonstrated the importance of clear, immediate scientific communication that acknowledges genuine mysteries while avoiding sensationalized interpretations that mislead public understanding. The data pipeline innovations developed for 3I Atlas set new standards for coordinated astronomical observations. The real-time integration of data from Hubble, Webb, SPHERICS, and ground-based observatories has created unprecedented synergies where each instrument's capabilities complement the others. This collaborative framework provides a template for studying future interstellar visitors, ensuring that we maximize the scientific return from each brief encounter. The industrial and academic partnerships forged during the 3I Atlas campaign have established new models for target of opportunity observations. The traditional astronomical culture of carefully planned, peer-reviewed observing programs has proven too slow for studying rapidly evolving interstellar visitors. Instead, we've developed rapid response protocols that can redirect major facilities within days of discovery, transforming competitive telescope time into collaborative science platforms. The theoretical framework for understanding interstellar visitors has expanded dramatically since Oumuamua's discovery, incorporating insights from planetary formation theory, astrobiology, and even speculative physics. 3I Atlas has added carbon dioxide chemistry to this framework, creating a more complete picture of the possible chemical environments where planetary debris can form. Future visitors will test and refine this framework, potentially revealing formation processes that don't exist in our own solar system, The philosophical implications of interstellar visitor studies extend beyond astronomy into fundamental questions about the nature of planetary formation and the prevalence of life in the universe. If the chemical diversity we've observed in just 3 visitors reflects the true range of planetary formation environments, then the galaxy harbors a vast library of different chemical recipes for building worlds. Some of these recipes might favor the emergence of life. Others might create environments utterly hostile to biological processes. The technological development driven by interstellar visitor science has accelerated innovations in several fields. Improved spectrometer sensitivity, faster image processing algorithms, and more sophisticated orbital mechanics software all benefit from the demanding requirements of studying faint, fast-moving targets. These advances will enhance our capability to study not just interstellar visitors, but the full spectrum of small body populations throughout the solar system. The international cooperation that 3I Atlas has inspired provides a model for addressing scientific challenges that transcend national boundaries. When the universe delivers phenomena that require rapid, coordinated response, the astronomical community has demonstrated remarkable ability to set aside territorial concerns and focus on shared scientific goals. This collaborative spirit will prove essential as we prepare for future interstellar encounters that might arrive with even shorter notice. The educational impact of interstellar visitor discoveries has already begun reshaping how we teach planetary science and astrobiology. Students learning about planetary formation now study examples from other star systems, not just our own. The chemical diversity revealed by 3I Atlas and its predecessors provides concrete evidence that planetary environments can differ dramatically from the Earth-centric examples that once dominated textbooks. As we prepare for the next interstellar visitor, the lessons learned from 3I Atlas extend beyond technical capabilities to encompass the intellectual frameworks needed to interpret genuinely alien phenomena. We've discovered that our theoretical models, developed from solar system examples, may be incomplete guides to understanding material from other stellar environments. The next visitor might challenge our assumptions in ways we haven't yet imagined. The cosmic perspective that emerges from studying interstellar visitors is both humbling and inspiring. We live in a galaxy where planetary debris regularly crosses the boundaries between star systems, creating a slow but steady exchange of material that connects distant worlds across light years of space. 3I Atlas represents just one thread in this vast cosmic web, but studying it reveals the intricate patterns that bind our galaxy together. The universe keeps sending us these messengers from the deep, each one carrying news from regions of space and time that we can explore in no other way. Our response to these cosmic gifts, the science we extract from brief encounters with wandering worlds, will determine how well we understand our place in the galactic community. As we watch 3I Atlas disappear into the solar conjunction blackout, we're not just losing sight of a single visitor. We're preparing for an era when such visitors become regular features of our astronomical landscape, when the space between stars transforms from mystery into familiar territory populated by samples from 1,000 different worlds. The next messenger is already out there, somewhere in the cosmic dark, following its own ancient trajectory toward our solar system. When it arrives, we'll be ready. Thank you for spending this time with us tonight here on the Sleepy Explorer. If you enjoyed this journey, don't forget to subscribe so you can drift off with us again on the next adventure. For now, we wish you a peaceful night's rest. Good night, and thank you for tuning in.